Well, the first thing you'll notice when the computer screen comes up is that, if you can put the computer screen up, please, is that the title of my talk is different than was just announced, and I'll explain that in a minute. The Inamori Foundation asked all of us to look back in our past to try and talk about motivations, some inner feelings and so forth, and that is very difficult. This old mechanical fortune teller in a play by Thornton Wilder says, "I can tell the future, nothing easier, but who can tell the past?" And if you think about it, the future is actually kind of easy because it hasn't happened yet. And we can be vague about it and still be in the right neighborhood. But the past is messy because it has happened and it is very detailed and the details all mesh together, and it's very difficult to make even a short or a long talk coherent because so many things have to be left out. But this approach today will look just at a few ideas from when I was young. And I think the most important thing that happened to me in my entire life was learning to read several years before I went to school, and learning to read fluently. And this was an accident, I think, because of the way my parents read to me. But I also grew up in a house full of books, and so the world of reading, even when I was 4 and 5 years old, was very, very rich. But when I went to school a few years later, the environment was almost a desert. There were very few books. The books were very rudimentary. And much worse than that, there was a single book for each subject that was the only book that was the authority, according to the teacher. And of course, I had already read a few hundred books by then, and when the teacher would say, "This and so," and I would raise my hand and say, "But I read that these people say something different." And pretty soon I realized that the teacher was getting very angry when I did this because she wanted the kids to learn what was in this one book. And that left a lasting impression on me. But I had found that if I wanted to learn something, I could do it myself. And so school was only a bit painful, not completely painful. Then, when I was in 4th grade, I had a completely different kind of teacher. Mary Quirk was her name, and her classroom was kind of conventional, except that in one corner of the classroom was a table completely filled with junk. So wires and pipes and hammers and nails and screwdrivers and bottles and dry cell batteries and books. And she never referred to this table. She never gestured towards it. She never talked about it. So naturally I got curious and started poking around this table, and I found a little book on electricity that showed how to make an electromagnet. And so one afternoon in English class, I had my English book set up and the little electricity book behind it and the dry cell batteries behind that, and wrapped the wire around the nail, and sure enough, it was able to attract some paper clips. And I let out a shriek. It works. Now, most teachers would have punished me for interrupting the class, but this teacher stopped the class, came over and asked me what I'd done and were there more things that could be done. I said, yes, there's more things in this book. And she asked other kids in the class if they were interested, and some of them were, and she set up a little group to explore electricity. And this happened every few weeks. with different kids, would find something on the table, they would get excited about it, and this marvelous teacher would set up a little group of kids who are interested in this, and pretty soon about half of the time we spent in fourth grade was working on these little projects with deep intensity. And we started coming earlier and earlier to school, and as early as 6:30 in the morning, but Miss Quirk was always there. We could never beat her to class. When I got to graduate school many years later, a wonderful graduate school, I realized, oh, this is just like my fourth grade class. And then I realized something better is that this teacher had made her fourth grade class like a good graduate school. And she'd realized that children are in the state of not knowing the world very similar to scientists. And that they needed to explore this world, and they needed to do it for their own reasons. So most of the things that I've learned about education started with this marvelous teacher. Now, of course, she was the only marvelous teacher I had in 12 years of primary and high schooling. So that was very disappointing. But having one great teacher makes all the difference. And then a year later, I got very interested in these vacuum systems, pneumatic tube systems for holding money and messages that were in some of the stores. And I asked adults, well, how do they work? And the adults said, well, vacuum. And I said, but how does vacuum work? And the adults said, well, vacuum does it. No explanation at all. And so one afternoon, I took my mother's vacuum cleaner and took it apart. And inside it, I found a motor, which I'd expected, but the only other thing that was in there was a fan. And I had not expected that. I expected something else, some elaborate mechanism. And by taking the bag off, this end blew air from the fan, which seemed reasonable, but it wasn't clear what was going down at this end that seemed to be sucking. So I looked at a fan, and the same idea is that it's pretty easy to understand what's happening in the front of the fan, because you can think of it as hitting little balls. So if you move the fan blades up, they're going to push the little particles of air off. But what is going on behind here? Is there some mysterious force that creates something that sucks things? So I put a cardboard housing around the fan and tied it up with electrician tape and put a little hole in it, and sure enough, there was some suction, but I couldn't figure out what was causing it, because my image of air molecules was that they were just drifting around, just slowly drifting around. And then I suddenly realized that one way of explaining what was going on was that the air molecules were moving very, very fast. And they were actually bouncing into each other. And they were doing it in such a way that we didn't feel any net breeze from them. But if the fan blade could get rid of air molecules, then these random movements would actually appear to be directed. These air molecules would appear to know where the rarefied part of the fan was, and they would stream in there. But actually, they were just expressing their motion. And so when my father got home that evening, I said, "Dad, the air molecules must be going at least 100 miles an hour." And he was a physiologist, so he got out his physics book and found the formula and calculated out that the air molecules are going, some of them are going as fast as 1,500 miles an hour, maybe 2,200 kilometers per hour, really, really fast. And that completely shocked me. And I think this is the first real scientific exploration that I did where my common sense way of thinking about things, which was like everybody else's common sense, that vacuums are somehow sucking things, was completely turned around by thinking about a completely different way of explanation of why the air molecules flow the way they did. And another thing I was interested in when I was a child was drawing and painting. My mother was an excellent draftsman, and I also got interested in music. And it was a couple of weeks ago, playing the pipe organ here, that I realized that I did not like the original lecture I'd sent to the Inamori Foundation. So I was playing this great music, and I was not explaining in this lecture what the music of computing is. So the lecture I'm giving today is an attempt to explain a bit of the music of science and technology, because the reason people get interested in science and technology is very often because of its artistic content. And most people don't think of science as an art or technology as an art form, but all three of these areas are actually art forms. The ones we're most familiar with are over here on the left-hand side. And you can see that these three categories here are roughly the three categories of prizes given by the Kyoto Prize Committee. And here I've grouped them according to who are the ultimate critics of the art forms. So in the traditional art forms, nature actually just doesn't care what we write on a piece of paper. We can write anything on a piece of paper, and we can write it also with the word not. So we can write things that are like what the universe is, and we can write things that are exactly the opposite, and we can make up new universes. And that's true for all of these areas. So over here, the ultimate critics are human beings. And science is only a few hundred years old. And over here, the ultimate critic is only nature. It absolutely does not matter what human opinion is over on this side if you're doing science. It's only nature can give you some sense of how good the theories are over here. And the art form on this side is the art of not being fooled and the art of making models and theories about what we think is over here. Then in the middle are technologies which combine both of these. So for instance, a bridge has to heed nature because we don't want the bridge to fall down. So we can't make a bridge that is against nature because it won't be a bridge. But we also like a bridge to be beautiful, and so we're concerned with the form. And technologies tend to be processes that are worried both about nature and form. So an example of a technology that worries about both of these is glass blowing. I have a friend who's a glass blower, and he told me once that if he could, he would eat the molten glass. He wanted more than anything else to be able to bite into it. And I think that's a very good way of explaining how artists feel about what they're doing. It's a great human trait to be able to love other people deeply and romantically. And artists are people who can love ideas and the expression of ideas as deeply and romantically as they can love other people. And my friend, Bill, loved his glass. And he didn't just love it after he had made it into something. He loved it while he was making it, and he wanted to become it. He wanted to ingest it. Now, modern glass blowing is actually the creation of computer chips. So, for example, here's Bob Noyce, who is one of the founders of Intel, and here's a big wafer full of computer chips, and the principal ingredient of glass is silicon, and the principal ingredient of computer chips is silicon. And we can see that these chips are quite beautiful here, but the real beauty of them is what they do and how they're fashioned at the micro level. So it's hard to explain the beauty of them in a few sentences. Now, when we turn to science, we go to a more complicated process. Science, one way of thinking about it is it's the art of not being fooled. And we can see this frog here. What we've done is taken some of the frog's food, flies, and paralyzed them with a little chloroform and put the paralyzed flies in front of the frog, and the frog ignores them. In fact, even though these flies look like flies, even though they're alive, even though they would be good for the frog, if the frog ate them, the frog will not eat them. Because the frog is born knowing a very, very simple thing about its food, and that is its food is a shape that moves. And so if you throw cardboard at the frog will eat the cardboard until it is completely stuffed with cardboard, even though the cardboard is not good for the frog. Now, of course, we're not frogs. Or are we? I know some people who are rather like the frog ingesting the cardboard that's not good for them. And in fact, human beings are easily fooled. And in fact, we like to be fooled. So we go to the theater to be fooled. We read novels to be fooled. We listen to political leaders to be fooled. So it's built into us to actually live a kind of a story rather than do what science does, which is try not to be fooled. And an easy way of showing this is to show an example from our friend, the great drawing teacher, Betty Edwards, who starts her drawing class off with these two tables and says to her class, now, the reason that you may be having trouble drawing is not because you can't move your arm. It's because you're trying to recognize things too much instead of looking at the shapes and the edges and the spaces. And to illustrate that, she says, for instance, the size and shape of these two tables is exactly the same. And the class says, no, that can't be. This is long and skinny. This is narrow and fat. And she says, well, take a look at this. If I take this top from one table and I just rotate it around, what do you think just happened there? And notice that even after I did that, you still can't see that they're the same. In fact, I've done this hundreds of times and I still can't see that they're the same. But if you want to verify that they're the same, take an object like a pen and hold it out in front of you, and especially if you're sitting in the middle, you can measure the edges and compare them, and you'll see that the edges are exactly the same. But your mind, your ability to recognize things won't let you see the shapes as the same. So that's a very, very good metaphor for the difficulties that science has. And there's a nice saying from the Talmud, we see things not as they are, but as we are. That is, whenever we're looking out into the world, we're always seeing ourselves. We're not really seeing what's out there. We have to learn very carefully how to see what's out there. And another nice metaphor for science and part of early science is map making. So here's a map of India on the right, and on the left is a map of the world that Tolkien created for The Lord of the Rings. And I can't tell, and neither can you, by looking at these detailed maps, which one is real and which one isn't. I have to rely on faith that there is a continent called India, and this is what it looks like. I've never been there. I've never seen it from space. And I also have to rely on faith that there is not a place called Middle Earth. So these maps are stories, and what science does is to try and make maps that are supported so strongly that we can rely on them more than regular stories. So another example of this is to take some phenomenon out in the universe, like this bunny that we can't see directly. We can only see the shadow of the bunny. And let's think of the bunny as being gravity. And the shadow of the bunny is that part of gravity that we can sense with our senses and our instruments. And then we try to understand the bunny by making a model that will cast a shadow that's as similar as possible. So, for instance, we can make one with our hands in this case, and this could be, for example, Newton's theory of gravitation, which casts a very nice shadow. It looks like a bunny in all respects. Till a little over 100 years ago, by studying the orbit of the planet Mercury, they discovered that the real shadow had a little tail on it, and when they looked at Newton's theory, they discovered an arm sticking out. So they realized that Newton's theory of gravity wasn't the truth, as they had thought, but only an approximation, and a very, very good approximation. And Einstein got the next best set of models and shadows, and he said something very important. You must learn to distinguish between what is true, that is, the things that can be done in mathematics and stories, things that are logically consistent, and what is real, what's out in the universe. And here's a longer one that he said. He said, as far as the laws of mathematics refer to reality, then they are not certain. And as far as they are certain, they do not refer to reality. And if you think of this in the larger sense, it means that for efficiency's sake, we think that our perceptions and beliefs are reality, and we act that way. But in fact, we found over and over again that that is not the case. And that means that a very good strategy for all of living is to insert thought between perception and action, because we're usually wrong. So some marvelous things started happening. In 1780, in the UK, you could get a pocket globe that showed the Earth as it appeared from space. And 200 years later, we went out into space and took a picture of the Earth, and it looked exactly like the pocket globe. So science was able to make the invisible, the thing we couldn't see, visible 200 years earlier than we were able to go out and look at it directly. So that's a much stronger way to look at science. Besides trying to help us not be fooled, it tries to make the invisible visible. Now here's a modern version of this. A Japanese molecular biologist, Dr. Kinoshita, I contacted him through the internet because I was very interested in that he was taking tiny molecular motors that are in bacteria and attaching huge objects, actually 1,000 times larger than this, to them so you can actually see them in a light microscope. So here's a huge object attached to a molecular motor that you cannot even see. And this is used to wave the flagella of a bacterium. Mathematics is beautiful, but most people never experience it in school. This is Newton's theory of gravitation here, and it's very, very beautiful. Some people think that if a formula about the real world is beautiful, then it must be true, but in fact, that's not the case at all. It's beautiful because we think it's beautiful, and we need a different formula to describe gravity better. Famous Maxwell's equations, which I won't try to explain, but I think I can show you something here with the theorem of Pythagoras, which everybody has encountered, but usually not with a beautiful proof. And this might be Pythagoras' original proof. So the idea here is, the conjecture is that the area on the long side of the triangle is equal to the area of the two squares on the short side. And this is a way that fifth grade children can discover how this works. So if you put 3 more triangles around this c squared here, you copy it, you can rearrange the triangles so that there are still 4 triangles inside this area, and we can see that these 2 C areas here must be the same, because this is a big square with 4 triangles, and this is the same size square with 4 triangles. And this little shape here looks kind of suspicious, so we should be able to move the a squared and the b squares over there and exactly cover that space. And this is a demonstration and a proof of this beautiful work of mathematics done 2,500 years ago. Now, a beautiful thing in computing was done by the Kyoto laureate John McCarthy around 1959 and 1960. And I spent a fair amount of the summer trying to figure out how to explain this. It is really beautiful. It is really powerful. It gave all of us hope that there could be a real mathematical theory of computation. And instead, I'm not going to try to explain it. But I will show you something visual that I think is very beautiful also. And this is the first computer graphics system done in 1962 by Ivan Sutherland. And everything that you see here is new. So to get the computer to actually make lines, he had to write a program. Here he's pointing at the edges, and he's telling the edges, well, straighten up and be mutually perpendicular for me. And you can see that the system did that for him. He wants to draw a little flange. So again, he draws 2 lines, tells the computer to straighten them up. And then he uses them as guidelines for making dashed lines. And the power of this first system was tremendous. For instance, he could draw in a bridge without the system having to know anything about bridges, tell the system a little bit about how the beams in bridges respond, and then put a weight on the bridge and would get a simulation, a dynamic simulation of the bridge sagging under the weight. And this completely captured my imagination as to the way computers should be used, both for simple things and for terribly important things. The ability of the computer to simulate complicated ideas goes far beyond classical mathematics in its range. And it was the combination of that, being part of the ARPA community that was working on the forerunner of the internet at that time, seeing some other work, and having been a former biologist and a mathematician, that got me thinking about the entire world of computing being represented by little machines just sending messages to each other, that at all levels of detail, all levels of scale. Now, a couple of other wonders that were around at this time were my vote for the first personal computer. No, I did not do the first personal computer. I gave it its name, but we already had this one to look at, done by Wes Clark, and we had this marvelous system, the first pen-based user interface.
First, we erase a flow arrow Then move the connector out of the way so that we may draw a box in its place.
So it recognizes he wants a box and makes one. Now it's recognizing his handwriting.
The printing in the box is being used as commentary only in this case. The box is slightly too large, so we may change its size.
So even by today's standards, this system was tremendous. We wish we had something like this today. And so you can get an idea that there was an air of romance and extension and power in these early conceptions. Another one was by Doug Engelbart, who is well known in Japan, who invented the mouse, but he invented it for a very high purpose.
So I can say, I'd like to go to produce, but I'd like to go to produce, they get big, I'd like to say one branch only, and let me look just that low, and I see it. Oh, I can say, I'd like to see one line only. I can see it. But there's another thing I can do. There's a root I said I have here. So here, I'm afraid I'll need a different picture of the view. So here's what I drew with a picture drawing capability. Here's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that.
So the invention of linking and many of the things you're familiar with today, but done with the idea of helping groups working together. And one of the things they showed in 1968 was this.
Like that leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work, you can point at it, and I can see your face, and we can talk.
So the idea of close collaboration between people who are many miles apart, sharing the screens and everything, was born a long time ago. So this is a very romantic time, and a friend of mine and I started making a desktop machine that looked like this. This is a self-portrait on its own display. And while we were building it, I visited Seymour Papert, who had started working with children, and found that he had done something really remarkable. Papert was a mathematician who had also studied with the psychologist Piaget, and he discovered that children were very, very good at a form of mathematics called differential geometry. So, for example, if a person is going to draw a circle, there are many ways of doing it, but if you want a 5-year-old to do it, just ask them to close their eyes and make a circle with their body. They'll do this. And you say, well, what are you doing? And the kid will say, well, I'm going a little and turning a little, over and over again. And here in Logo, going a little is forward 5, turning a little is turn 5, over and over is repeat. And so if we get the turtle on the screen to do that, we'll get a perfect circle in a method that was invented by Gauss about 150 years ago and is the main mathematical language of science. So that completely captured my imagination, because I thought this is the best idea anybody had ever had for what to do with computers, which is to help children learn to think better than most adults do today. And so I made this little cartoon on the plane ride home and built this cardboard model and started thinking of the computer not as a tool or even like an automobile, but as a new medium, something like a musical instrument whose music was all of ideas. And that gave a tremendous amount of motivation to start making these ideas happen. So at Xerox PARC, we started thinking about making a little machine that we could make a few hundred of, and we had a problem of software. There was a bet, and because I knew what McCarthy had done, I said, well, I can write down the most powerful language in the world in a half page, and this is my object-oriented version of John McCarthy's technique, and a month later we had it running, and we all of a sudden had a language called Smalltalk, and one of the first dynamic object-oriented languages. And then a bunch of us at Xerox PARC not just me, but many of us, about 25 of us, together created the basic inventions of personal computing today. But our aim was to get computers into schools. And I'd like to show you just a few, give you a little taste of what children do today on these machines. In fact, I'm using a little 2-pound laptop to give this presentation. And so one way to think about children is that all children are artists until they're talked out of it by society. And if you want to educate children, try to keep their artistic motivations intact. Don't try to be too practical with them at first. Instead, try to get them really interested in ideas. So a kind of project that 9-year-old children, 10-year-old children really enjoy is to make a car, design a car they would like to learn how to drive. So this is a kind of an example here. And both boys and girls like big off-road tires. I'll put some big tires on here. And my result here is a graphic object, and I can do things with it, but the most important thing with this is that I can look inside of it, and I'll call this car. And here are some properties of this car here. Go forward, so I'll click on the little exclamation point, it goes forward. Turn. And if I want to make a script, I just grab out these little lines here and drop them into the script and click on the clock here. So it's going forward by 5 and turn by 5. And if you remember, that was what Papert taught children years ago. So, and every one of these little objects that we make here is actually a little logo turtle in disguise. And we can investigate what happens here. So suppose I say, let's go turn by 0. I go straight. Turn by negative numbers, I turn like that. And what we'd really like to do, though, is to steer the car. So what I'm going to do is turn off the pen here, and I'm going to draw a steering wheel for the car. And what I want to do is to investigate, make a steering wheel like this. And again, I'll look inside of it, call it wheel. And here's a property of the steering wheel right here called heading. And it's where the steering wheel is pointing. So right now it's pointing to north, so the heading is 0. But if I pick up the name of the heading and drop it into the script here, and I turn the steering wheel, now I'm generating negative numbers, you can see here. The car is turning one way, positive numbers turning another way. And this is the way 4th and 5th graders learn about the concept of variables very, very painlessly and quickly. So our object is to teach them math and science, but especially thinking. After the kids have done a few things, we encourage them to come up with a project on their own. So here's an example of a project made up by a child.
I did something different from cars racing. Instead, I made pigs racing.
And they're off.
Here we go for the annual pig race. It looks like it's a rough time today. The pink pig crashing into the wall. My watcher here has told me what speed they're going. Oh, and the blue pig's coming in the lead. I have my own pig. I named it Jackson. And usually it loses. But oh look, the black pig is catching up, leaving the white pig in the dirt.
So these are the kinds of projects that kids make, and many of them don't realize that they're doing advanced mathematics while they're doing this. Now, to look into the physical world, we have to go out and do experiments.
That you think will fall to the earth at the same time? Okay. Oh, do not pay any attention to what anybody else is doing.
So the kids think that the heavy objects will fall the fastest.
If you run away from it, it will.
Who's got the apple?
Drop.
What'd you get? What'd you get?
That apple classroom.
0.99 seconds.
Together. So put sponge ball.
Okay. I think we should do the shot put and the sponge ball because they're two totally different weights. And if you drop them at the same time, maybe they'll drop at the same speed.
Drop.
So in every class, you'll usually find one Galileo child. This was a little girl who realized, well, you don't really need the stopwatches. Just drop the heavy one and the light one and listen to see if they hit at the same time. But the detailed study of falling objects today is much easier because we can take a video of them. But even when we look in the video and try to understand what's going on, it's hard, even when we single-step the video. But in fact, we can pull out the frames of the video, and that's a little more suggestive, and we can stack them up like that, and that's even more suggestive. We can see that a greater distance is being traveled in each equal time interval, and if we measure from the bottom of one ball to the bottom of the next ball, the heights of these rectangles are actually the velocity in that particular time interval. So this is a nice way of measuring without having to use numbers. And if we stack these up like this, we get an easy way of comparing them. So the difference in velocity between this one and this one is this little patch here. The difference here is that and that. So the changes in velocity looks like they're constant over time, and that leads to a very simple little script here. And let's listen to Tyrone explain it.
And to make sure that I was doing it just right, I got a magnifier, which would help me figure out if the size was just right. After I'd done that, I would go and click on the little basic category button, and then a little menu would pop up, and one of the categories would be geometry, so I click on that. And here it has many things that have to do with the size and shape of the rectangle. So I would see what the height is. I kept going along the process until I had them all lined up with their height. I subtracted the smaller one's height from the bigger one to see if there was a kind of pattern anywhere that could help me, and my best guess worked. So in order to show that it was working, I decided to leave a dot copy so that it would show that the ball was going at the exact right speed and acceleration.
So in fact, he's doing something like this to show that the simulated ball and the real ball in the movie are exactly tracking each other. So that's the way children do science. And by the way, in the United States, about 70% of the college kids who do that fail to understand it. And it's not because the college kids are stupider than the fifth graders. It's because the context in which most college kids are given to learn these ideas is a very weak one. So here's another thing that you can do very powerfully with computers, and that is to get zillions and zillions of little objects. So these are like little cars. I've got a little red one over here you can see. And you can think of an epidemic as like spreading a rumor. So this little red guy has a secret, and every time he touches a blue guy, he's going to tell the secret to that blue guy and have the blue guy turn red. And so what happens here is a something that happens very, very slowly at first, and then it just explodes, and then there are no more blue guys left, and you get this characteristic curve. The danger of AIDS is not understanding this front part of the curve. We'll talk more about this tomorrow in the workshop. Okay, so my last example here is an idea about springy things. Because there's so many things in the world that are springy, not just physical, simple physical objects, but much of the transmission of radiation is also springy. In order to understand how this works, we have to, if we think of a weight here as exerting a force downward, then it is very, very hard for most children and adults to think of, when we put it on a table, that the table is exerting a force upwards. Because we think of a force as something that has to do with movement. But the way science thinks of this is the table is exerting a force upward. We can get a better idea of it by putting the heavy weight on a lightweight table like balsa wood, and it'll sag until it can exert the force upwards and stop the weight. If we use a very, very lightweight table like a paper table, it just collapses until it goes all the way down to the floor, and then the floor exerts the force upwards. And the same thing happens with beams here, that a stiff beam will not appear to bend visibly, but a weaker beam will bend. And springs are well-behaved versions of these. So if I hang a weight on a typical spring here, it'll stretch the string by a length d, and if I take twice the weight and hang it on the spring up to a certain level, it will stretch the spring twice as much. And that gives us a very easy way of calculating the force that the spring is exerting. And so we can write this little script that just says the acceleration on the weight here is going to be proportional to the stretchiness of the spring at any given time. So if we tell this guy to go, it's hard to see what's going on, but if we move it along and just let it be its own little plotter, we can get a good idea of what a spring actually does. Now, I've been using bridges as my theme, and a very famous bridge to everybody who's ever studied engineering is this one near Seattle. And one day, it's called the Tacoma Narrows Bridge, and one day a wind of over 100 miles an hour came up and started blowing this bridge, and the bridge started swaying. And fortunately, some people went to a camera shop and got a color camera and started taking movies of what was actually happening here. So this is solid steel, but bending as though it's made out of cloth. And the bridge handled it for a long time, but then started breaking up, all in the period of a couple of hours. And of course, the people who designed this bridge did not intend for this. This was not their objective. They wanted a beautiful bridge, but they also wanted one that works. And it's interesting that today a child can model a bridge. So here we have two springs and a weight. This is exactly the same little script that I showed you before. We're letting the weight stretch down these two springs. And if we turn on some wind, it'll blow the weight over and it'll steady down. Nothing too dangerous there. But what if the wind is gusting? So I'll turn the fan on and off here. And all of a sudden it starts getting unstable. And that's what happened with this bridge, that it was actually not stiff enough. It was a little bit too springy, and the wind got it going in a resonance condition, very much like a tuning fork or the string on a piano. Now, just in the last few seconds, I'd like to show you something more like a real bridge, and also just to show you that we have many more dimensions than the two that you're used to on a computer. Tomorrow we'll talk more about this environment, but here what I'm going to do is just come around here and make a more interesting bridge. So here's our bridge. And the first thing we want to do is to get gravity turned on to this bridge. So I'll say, okay, go ahead, turn gravity on now. You can see it start to sag. The next thing is I want to make the bridge more springy, like the Tacoma Narrows Bridge. So I'll change this little script here. You can see it sagging a lot more. Now I need to turn on a wind. And this little script will make the wind gusty, like we were talking about. So turn the wind on. And we can see it starting to act like the bridge. In order to see it better, I'm going to come around and look at it end on here in this three-dimensional world that I can construct things in. And so when we first did this, it looked like, wow, this is like cloth. This doesn't look like a bridge at all. And that gave us an idea that cloth and bridges are very similar. Sorry. So the romance of computing is to be able to understand complex ideas through a new kind of art form where we make our ideas, and our ideas are art, and the understanding of these ideas are art. The Greeks held that the arts were the imitation of life, but the computer arts are the imitation of creation itself. And it's the romance of this that draws kids to learn how to think better than any children have thought before. That is our romance, and that is the center of my why for doing this. Thank you. Thank you.